This video will focus on decarboxylation. Decarboxylation is a process of heating either plant or cannabis extract to low temperatures to convert the carboxylic acid structure of cannabinoids into one that doesn't have the carboxylic acid. So that's converting THCa into THC or CBDa into CBD. And it's actually a chemical reaction, and it's really making the CBDa and the THCa psychoactive, because with that carboxylic acid group that's here circled in red and I'll highlight it blue on the THCa, with that present on the molecule, the THCa molecule doesn't cross the blood-brain barrier as well. Once it's removed, THC is much more capable of crossing that blood-brain barrier, and therefore we see more psychoactive effects from it. And so this, it's the same part in both the CBDa and the THCa molecule. And this will happen over time, but with the application of a little bit of heat, the carbon and two oxygens of that carboxylic acid will form carbon dioxide. So this is really also producing this. And then in this spot right here where we had the carbon and the two oxygens and hydrogens, we'll have just a hydrogen bonded to the carbon of that six-membered carbon ring with the alternating double bonds. Same here with CBDA, it's the same reaction. It releases carbon dioxide, leaving behind a hydrogen. And actually CBGA also does this same conversion to CBG. THCVA will convert to THCV. And so our cannabinoids that are in this carboxylic acid form will all convert to their more psychoactive form. And when we think about the actual plant, most of these cannabinoids are in the plant and stored in the plant as the carboxylic acid. And so this process is really necessary to activate all of the benefits of the cannabis plant. So what's interesting about this process is that it will happen over time on its own. And it's actually part of an overall process that's happening where the THCa or CBDA is being decarboxylated to THC and then undergoing an oxidation to form CBN. And so this will happen slowly over time, or we'll see that it happens during the curing and drying process as well. It can be accelerated with light or with heat. And so that curing, drying phase exposes enough the plant to enough light and heat that it will decarboxylate a lot of the cannabinoids. But also, and we can do this with the plant, and we can also do this with extracts, just heating at a very low temperature will accomplish the same goal. So what's interesting about this process that's occurring of decarboxylation and oxidation that'll happen over time is that we have the majority of these components are actually not psychoactive. So our THCa is not psychoactive, or very, very mildly so. THCa does have other benefits, but from ingesting it, but you don't get that same feeling that you do when you have ingest THC. And so then THC is psychoactive. But then as this oxidizes to CBN, it then loses that effect. And this is then only mildly psychoactive. So there really is this kind of like perfect place where you have you want to optimize to have THC rather than THCa or CBN. CBNA, there's another route to CBN as well. Some of our THCa will oxidize just to CBNA and then decarboxylate to CBN. And when we're looking at this oxidation component, what's changing here is this six-membered ring right here. And or you can also see it on this one over here. And we're forming double bonds and losing some of our hydrogens. And so that oxidation process is the loss of hydrogens. And so you can see we form a double bond here. And then we also form a double bond here. And are losing essentially 4 hydrogens from the molecule through that oxidation process. Remember, these alternating double bond, single bond, double bond, single bond, especially six-membered rings, are very stable. And so there is this natural drive to optimize the stability of the molecule. It'll be at just a general lower potential energy. And so that six-membered ring is something that'll just happen naturally, spontaneously over time, even though it happens slowly. Another thing to point out here, and this is focusing on THC, but what's interesting is that they've seen that the decarboxylation rate for the reaction, like how fast it occurs, is faster for THC than CBD or CBG. They both happen in the same way, but the rate is a touch faster for THC. So to really enjoy the effects of THC or CBD, the plants need to be decarboxylated to be able to increase the amount of THC or CBD that will produce those psychoactive effects that are so many of the benefits of the plant. So that decarboxylation process may be occurring through just the method of ingestion. And so any method that's going to heat the material above 250 degrees Fahrenheit or 122 degrees Celsius is going to decarboxylate the cannabis material. And so things like smoking, vaping above 250 degrees Fahrenheit, which most vaporization is happening more around like the 300 degree. Dabbing, which is at even higher temperatures than vaping. And even baking, if you're baking a cannabis product into an edible at 350 degrees in your oven, that decarboxylation will happen. So that leaves a few methods of ingestion, though, where this decarboxylation step needs to be performed in the production of the material. And so that's going to be for our extracts that are going into edibles that are not going to be baked, like gummies and candies, although some candies are heated. Also in beverages, or if it's being put into capsules, or the little tiny strips that dissolve in your tongue, or tinctures, or some capsules. Anything that's not going to heat it in the process of consuming it. So these all need to have a decarboxylation step before producing any of these products using a cannabis concentrate. So building on that reaction that we saw that showed THCa converting to THC, but then oxidizing to CBN, I'd like to talk for a minute about optimizing the temperature and the timing for decarboxylating cannabis extracts and plant materials. So, you need to optimize it to prevent that oxidation to CBN, which will reduce the overall THC content of your sample. So this graph right here is showing the conversion of THCa into THC, and it's looking at concentrations. So here's our THCa curve, and here's our THC, and we're looking at a percent conversion. So this is the amount of THC, or the percentage of THCa that has converted into THC. So as we increase, we have converted more. And so initially we have about 50% THCa, and we can see that as we convert, as we heat, as we increase the temperature, we'll convert our THCa into THC, and we see our THC increase as our THCa decreases. At a certain point, we get below 10% THC, and we have converted about 65% of that THC into THC. And then we hit this part of the curve at temperatures higher than 160, where we have no more THCa to convert. And what we don't see is this THC curve flatten, which I would expect. Instead, you start to see a decrease in concentration of THC at higher temperatures. And note that this is in degrees Celsius. And so that ideal temperature of 122 degrees Celsius was about 250 Fahrenheit. And so we're really looking at temperatures above that. And so what's happening here in this region of our curve is our THC is oxidizing to CBN. And so we're losing the potency of that compound by heating our THC to too high of a temperature. We're also going to see some of this vaporize at a certain point as well. So this graph is looking at different temperatures and optimizing for the amount of THC that's present in material. And so this is looking at THC content for a cannabis extract. Was actually using N-hexane, and then the solvent was removed, and then it was decarboxylated. And they tried decarboxylating at different temperatures and for different amounts of time. And they were tracking the amount of THC content per gram of the extract. And that's what's being shown here on the y-axis, is the amount of THC in milligrams per gram of extract. And then on the x-axis, we're looking at the amount of time that they heated the sample for. And so we can see that at higher temperatures, so 145 degrees Celsius or 293 Fahrenheit, we are actually optimizing, maximizing the amount of THC we have in our extract if we only decarboxylate for 7 minutes. After that, it decreases. We're going to see some of that convert to CBN. So if we're going to decarboxylate at a higher temperature, we want to make sure it's for a short period of time. Now, this is getting close to the amount of, or the temperature that we would vaporize cannabis products at, or these concentrates. And so keep in mind that it's not just at 145 degrees Celsius and above is this a problem. It's because then we wouldn't be able to ingest THC through vaporization, but it's really the amount of time. And so usually a sample isn't heated at its vaporization point for 7 minutes, right? It vaporizes really quickly. So if we lower the temperature and extend the time that we heat it, the next best version is this 122 degrees Celsius or 250 Fahrenheit about. And if we do this for 27 minutes, between 20 and 27 minutes, so here's 20, we're going to maximize the amount of THC that we have in our sample. And it's fairly close to the sample that was heated for 7 minutes at 145 degrees Celsius. And so if we lower the temperature further, then we really have to increase the amount of time that we are decarboxylating. And in fact, I would argue that we aren't really being productive at 94 degrees Celsius or 80 degrees Celsius. And we're only starting to be productive and maximize the amount of THC we have in our sample at 106 degrees Celsius or higher. So the best temperatures to decarboxylate at are either for a short amount of time at 145 degrees Celsius or for a longer amount of time, like 27 minutes at 122 degrees Celsius.